Now, why, we found the same thing, why does it have the shape that it is first increasing and then at the end
Right, so
it starts to cancel the...
because mentioned today in some other talks that you know, these matrix elements have phases, right? So
Yes,
they can
but
go
why is
up
it,
and down.
but why is it this way that at the...
It's not always this way. Sometimes it's only going up. It's not
Yeah,
always
but
this is calcium. But
listen,
my point is
listen, but finally you come to
so it's
some-
pretty much like the first state dominance, right? So because you get the same result, but it's not really the same, right? You go up and go down. And actually, this was. I don't have a picture with me, but the Japanese group, they actually did the experiment and they confirm our up to here, because up to here is the matrix element going up, and if they take the absolute value of these two matrix elements, they're going to go up like that.
We found this same thing 30 years ago,
Yeah.
and with the constellation and everything. But talking to Alex Brown a few weeks ago, he said he understands why it is
Maybe he does.
this way. Okay, but we
What I can
were
say is this happened not for all the nuclei, in fact.
not for all. No.
In some cases, going up, and with small wiggles, right? So the point here, there are 2 points. One is that you see this state is putting it down, pretty much. And after there are small little states because they don't.
But then at the very higher energies, you just run out of space, right?
No, you don't run out of space at all. But what happened is you actually have many states here, but it stopped because this comes with random up and down distribution. They don't.
At the small ones,
Yes.
yeah, they can
It's
fluctuate.
like a random contribution. Yes.
Is that not an effect of the spin-orbit partner that comes in as a with a different sign? Because from the energy you would match. So you have
Right, but could be, but but I cannot really predict that this is going to go down exactly the same way. That's my point. I mean, you are right. That's justified ups and downs, but that's my point is that you see it might happen that the final result is pretty much like the contribution from the first state without really being the first state. You don't really go there. And it's understandable when you go to higher energy here. First of all, this matrix element gets small, and they have random sign. They essentially don't add up coherently to change significantly your matrix element.
Yes.
I just want to ask about the ratio of heavy neutron exchange and light neutron exchange ratio, and because that heavy neutron is more, I think, high momentum component, and then it may be sensitive to how your tensor interactions are involved. And also I'm wondering, is that quite model dependent, I think, shell model?
It is, I mean, okay, so
and the ratio of
I think that the heavy neutron, actually, first of all, I was trying to convince you the first part is very important to have a good grip on that, because obviously that will tell us, okay, we can distinguish between the two effects potentially if we can exclude some others. So here, as I say, indeed, there is a humongous difference. So in this case, we really have to nail down better the short-range correlation. So, so DOE just awarded us about a couple months ago a topical collaboration grant. One of them, there are two main things we have to do is to nail down the GA, and the second thing is to have a good understanding of short-range correlation. I believe we have a good way of doing that. In essence, we can use the same technology which ab initio people use to renormalize the interaction. We can renormalize the operator. There's work in progress in that direction, and I hope that we're going to get rid of Bruckner and UCOM and stuff like that pretty soon. Yeah.
Yes, please.
Sorry, but this is a little bit to cure my ignorance about these things. If you look at the multiple decomposition, you have all these multiples in there, including the different spin and parities, I presume. So these are, when you say J equals 1, it has plus or minus parity, right?
No, these are actually, here the parities are okay, actually.
Yeah, I'm just asking. This is
but
you
so
can
this
calculate.
is 2 minus, this is 2 minus,
But
this
then,
is 1 plus.
But then later on, just when you look at the level scheme of one of these, you say that you only get the positive parity states. Where are the negative parity states?
For this is for selenium. In selenium we have the G9 half which can change the parity. In calcium, if you use PF, is only 1 parity.
Oh, okay, good.
So when you
Yes.
use DPF, now I have.
But if you go to the heavier nuclear, you have these
When you go to heavier
unnatural
nuclear, you
parity
always
sets.
your model space is between magic numbers, right? So in that case, you have different parity. Calcium is the only exception.
Yeah. Yes, I understand. Thank you, yeah.
Okay.
Any other questions or comments?